In this video, we're going to look at Gaussian elimination, which is a method that we can use to solve simultaneous equations. We're going to use it to solve these three simultaneous equations on the right. So we'll do an example on the right, and on the left-hand side of the page, we're going to discuss the method. So the first step is to write our equations in this matrix form, ax equals b. So in this, well, A is just a matrix. And then x and b are both vectors. X is the sort of x, y, z vector, and b is sort of the right-hand side of the equal signs in our simultaneous equations. So let's look at our example. Well, the matrix A are just the coefficients of x, y, and z. So they're 1, 3, minus 5 is that top line. The second line is 3, 11, minus 9. And then minus 1, 1, 6. Then we have the x vector, x, y, z. And finally, the b vector on the right-hand side is the right-hand side of the simultaneous equations 2, 4, and 5. So this matrix represented, it's exactly the same as the simultaneous equations. If we multiplied out that matrix equation, we would just end up with the exact same simultaneous equations. Okay, so that's step one. Step two is to create what's called the augmented matrix. Well, that's simply, all we do is we join the A matrix with the B vector. So the matrix A, 1, 3, minus 5, 3, 11, minus 9, minus 1, 1, 6, and we're going to join it. We're going to put a vertical line to join, and then we're going to follow with 2, 4, 5. And this augmented matrix step just makes the later part of the problem slightly easier. Okay. So now, the next step, which is really the crux of the problem, is we have to make A into an upper triangular matrix using what's called elementary row operations. So let's first look at upper triangular. So an upper triangular matrix is one that looks like, I'll draw a little arrow. So it looks like this. It has zeros below the diagonal. So for a 3 by 3 matrix, it has to have zeros down here, and then the upper right corner are just some values. It doesn't matter what values they are, just any values. The key bit is that this lower corner is zeros. And we're going to sort of apply these row operations to the augmented matrix. So we're still going to have an augmented matrix at the end. Okay, and so what operations we're allowed to use? We're allowed to swap any two rows with one another. We're allowed to multiply one row by a non-zero scalar, or we're allowed to add a scalar multiple of one row to another. They're the only operations we're going to use. And the idea is we have to create these zeros in the bottom left corner, and there's sort of a preferred order to do this. We're going to make these zeros that I've circled. We're going to make these 0 first. And then we're going to make this other one a 0 last or second. Okay. So let's apply it to our augmented matrix. And the key is that any operation we have to apply to both the left-hand side and the right-hand side. And we end up with this sort of new matrix rather than A, B, it's sort of A dash, B, B dash now. Okay. So first of all, we can make this 3 into a 0 by subtracting 3 lots of row 1 from row 2. So let's do that. So we're going to replace row 2, we're going to replace it with row 2 minus 3 lots of row 1. Okay, so what happens if I replace row 2 with 3 lots of row 1? Well, my row 1 is unchanged. My row 3 is unchanged. But my row 2 is replaced by row 2 minus 3 lots of row 1. So 3 minus 3 times 1 is 0. Then 11 minus 3 times 3 is 2. Minus 9 minus 3 times minus 5 is the same as minus 9 plus 15, which is 6. And 4 minus 3 lots of 2 is minus 2. So I've done that operation. I've replaced row 2 with row 2 minus 3 times row 1. And that's sort of, this is an elementary row operation because we've subtracted 3 lots of row 1 from row 2. Okay, and also we created a 0, which is good. So now we want to get rid of this minus 1 here that I've circled. So how do we replace that with, how do we turn that into a 0? Well, the easiest way is to replace row 3 with row 3 plus row 1. Because 1 plus minus 1 would be 0. So let's do that. So again, row 1 is unchanged. In this case, row 2 is unchanged. And row 3, now we're just going to add row 1 to row 3. So 1 plus minus 1 is 0. 3 plus 1 is 4. Minus 5 plus 6 is 1. And 2 plus 5 is 7. Okay, so we've made some progress. We've now got 2 zeros in this bottom left-hand corner. Now we need to turn this 4 into a 0. Well, to do that, we're going to use row 2, because if we use row 1, then this 1 on the first column would change the first column of row 3. So we don't want to use row 1. We want to use row 2. So how are we going to do that? We're going to replace row 3 with row 3 minus 2 lots of row 2. Because 4 minus 2 lots of 2 will give us 0. So let's do that again. Row 1 is unchanged. 1, 3, minus 5, and 2. Row 2 is unchanged. 0, 2, 6, minus 2. And row 3, we're going to replace it with row 3 minus 2 lots of row 2. Well, that doesn't affect the first column because 0 minus 2 lots of 0 is still 0. So that's good. We haven't changed that 0. That's what we wanted. Now the second column, 4 minus 2 lots of 2 is 0. Third column, 1 minus 2 lots of 6 is minus 11. And finally, 7 minus 2 lots of minus 2 is 7 plus 4 is 11. Okay, so we're now finished because this is in this triangular form, this upper triangular form. Okay, so now we can move on to the next step. Well, the next step is to solve what are now some easy simultaneous equations. So we can write our new matrix equation back as a simultaneous equation. That just says, the first line says x plus 3y minus 5z equals 2. The second line says 2y plus 6z equals minus 2. And the third line says minus 11z equals 11. Okay, well, we can solve these quite easily because of the format that we created with this triangular form. They become very easy to solve. We looked at the third equation first. Minus 11z equals 11. Well, that says that z equals minus 1. Okay. Now we look back at the second line. 2y plus 6z. Well, 6z is, if z is minus 1, this is 2y minus 6 equals minus 2. So that gives that y equals, well, 2y is equal to 4, so y is equal to 2. Okay, and now we can go to the back to the first equation. X plus 3y, so x plus 6 minus 5z, well, z is minus 1, so this is minus 5, this is plus 5 equals 2. So this was x plus 13, x plus 11 equals 2, x equals minus 9. And so now we've solved our simultaneous equations. Z is minus 1, y is 2, and x is minus 9. Now, if you have time, you can always check this solution by substituting back into our initial equations. Well, we can just do that quickly. I'm not going to do it for all of them, but let's look at this line. 3x plus 11y minus 9z. Three x plus 11y. That's what we're doing. Check 3x plus 11y minus 9z. And going back to the question, hopefully we should get 4 as an answer. Check by substitution. Well, this is 3, or x was minus 9, and y was 2, and z was minus 1. This is minus 27 plus 22 plus 9 is plus 4, which is correct. So it does indeed seem like we probably got the correct answer.